Okay, so I'm going to do this one more time because I think I had an error in my last code that I didn't notice. So I'm just going to run through this one more time just so that we make sure we have everything in here correctly. So I loaded up just the files here for the properties of water, and then we're just going to do the same thing, dp, just to get the properties of water in here. Okay, awesome. And then we're going to put in our parameters again. Total volume was 0.1, mass of the water 1 kilogram. This is just part A, the first part where we have one unknown and one equation, and then I'll do the 2 unknowns, 2 equations part afterwards. We have our initial pressure, which was our 5, final pressure, initial temperature, and our gas constant. Awesome. Oh, load those in there. Oh. Oh my gosh, typing too fast. Okay. Now we're going to put in the equation for the number of moles of air from the ideal gas law. So we'll just call N air equals, and we're going to first do the difference in the partial pressures. So we'll have the initial pressure minus the pressure in the vapor phase. Here we go, at the initial temperature, multiplied by the difference of the volumes. And in order to get the volume of the water, we have to do the density formula. And then all divided by R times the initial temperature. Oh my gosh. Okay, I guess you do need the multiplication sign there. Never mind. Alright, moving on. Now we can just go ahead and define our function. So we'll just call it pressure equation and do an x. We want the final temperature. We want it to give us the first value in the array. So that's going to be a 0. And then the volume in the vapor phase is the difference of the 2 volumes. So we'll do the total volume minus the same with the mass of the water divided by the density at the final temperature. And then we also need this partial pressures of the water. So the pressure of the water we can get from the Antoine equation, which is already loaded in our files. Just do that. And then the partial pressure of the air is going to be the PP equals nRT. Volume in the vapor phase. Alright, and then we want it to return. I just realized I didn't need to put that there, so that's probably all these things are messed up. Okay, return the sum of the partial pressures. Okay. There we go. Alright, so now we can use our root function that I loaded up here, and we can use the root function to solve the pressure equation for when the sum of the partial pressures equals 0. Awesome, and so we get the same value as before, this 366 number. Right, so now we are going to move on and do the second part of this problem, which is when we have two unknowns and two equations. So we're going to just go ahead and define a new function, and we have the x again, and I also forgot the colon there. Alright, and then we have the final temperature, which we don't know. We'll have it give us the first value, and then we also want the volume, total volume, which we don't know. Okay, awesome. And then we're going to put in our formula for the number of moles of air, which is the same as what we've been doing before. It's this initial pressure minus pressure in the vapor phase at the initial temperature multiplied by the difference in the volumes at the initial temperature. Okay, and then all divided by the gas constant times the initial temperature. Awesome, and then we also still need the we need to load in the volume of the container, the volume in the vapor phase, which is going to be the difference of the volumes, except this time, since we know the number of moles that we want in the vapor phase, we're going to be using that to subtract from the original mass of water. So we'll do this minus mass of the water minus moles of water, but we need to multiply it by the molecular weight of water so that we can have the same units. Okay, that's right, divided all by 1,000. And then divided by the density at the final temperature. Cool. Next, we need the partial pressure of the water, which is again just from the Antoine equation at the final temperature this time though. Then we need the partial pressure of the air, which is just the RPV equals nRT at the final temperature divided by the volume of the vapor phase. And then lastly, we need to use the number of moles of water in the vapor phase to equal the PV over RT. Okay, and then we wanted to return two functions that we want to go to 0, the sum of the partial pressures again. And then second, the difference in the number of moles in the vapor phase. Okay. And then we just want to make sure we put in the number of moles that it gave us, which is this variable, and then it was 0.3. Okay. And then we can go ahead and do our root function of the pressure equation 2, and then we have to put in our initial guesses. Remember, we did the final temperature as what we got from the last problem, which was about 360, and then our volume was 0.01. Where did I type VVA? Awesome. Why are those not the same values? I think I figured it out. I think I didn't have parentheses here before. so I'm hoping now once it has to be the quantity divided by the quantity of R times temperature, same with right here. So hopefully when I restart and run all, it will converge. Okay, yes, thank God, the solution converged. And here we have some more normal looking numbers. The temperature is positive and around the same value as from the problem before. Okay, so glad we got that done, and now I'm confident that this code is doing exactly what I want it to do. So that's good.